Okay. I'm hoping that people are going to join now. My apologies. This did not get started off well. I went to go, it kept messing up. That's all. I had it up. It was fine, and then I messed it up. So this is it. So hopefully you guys are finding this now, and that you guys are getting on to this Hangout. So until you guys get on and start putting in questions, I'm going to just start reviewing some of the essential skills that are in there. As you guys start getting on there and start adding questions, then I'll be able to answer those. So if we remember the essential skills, so I'm going to show those here for a second. I'm going to share them so everybody can see them. I'm having some difficulty making this screen come up. Okay. You can see that there are 4 essential skills. You have to perform calculations involving energy, wavelength, frequency, Planck's constant, and speed of light. And you write electron configuration or gas configuration. Also identify elements or ions based on the orbital notation. And finally, you should be able to calculate percent abundance and average atomic mass for elements. So I'm going to go through them. It looks like I'm getting a lot of messages. People are asking to join. Something I talked about in class is that I don't want you guys joining, I want you viewing. And I think I have a couple of viewers, but please stop asking to view, or stop asking to join. You need to go. You need to go to the link I sent to you guys and get on there. I gave you guys the link. If you view it through Google+, I don't know how else to describe that. So please take a look. I mean, if you're not a part of this, then you're not. Then you're not going to hear me telling you to not join. So anyhow, for those of you that are viewing, if you could type in questions if you have them. Otherwise, I'm just going to start going over some of the basics. And to do that, I have what's called a bamboo tablet that will write up as I am talking about it. Okay. So make sure that I'm doing this correctly. So essential skill number 1, and I'm going to change the thickness of this pen a little bit thinner. When we're doing this, we're dealing with, and I'm going to provide you, or some of it, if you guys remember the periodic table from the first test in Gen Chem, had formulas on the backside. And I'm going to provide you those formulas, which will make it a little bit easier. So the formulas that you need to remember, you have the speed of light is equal to wavelength times frequency. It's like C equals lambda nu. C is always a constant. C is always going to be equal to 3.00 times 10 to the 8th meters per second. Okay? So what that means is that the relationship between wavelength and frequency is inversely proportional. As one goes up, the other has to go down. All right, if you guys will give me a second, there's so many people asking to join. I don't know how to tell them to stop asking to join. I don't know if they're actually a member of the community or if they're Okay. All right, let's go back. I'm sorry. You guys are probably already there just waiting for me to keep talking. All right, so what that means is that if one goes up, then the other has to go down. And it's important also to know that your lambda, which is wavelength, has units that are usually they're in nanometers. Okay, and 1 meter equals 1 times 10 to the 9th nanometer. That's a billion nanometers. Okay, that's a lot of little tiny units. So if you're asked to convert from one to the other, you need to make a little bridge. So if you have, let's say, you have 483 nanometers. You make a bridge like this, and whatever unit you want to cancel out needs to go in the bottom right, opposite of it. So 1 times 10 to the 9th nanometers is equal to 1 meter, because it's an equality. This equality right here becomes a conversion factor here. It's sort of like, if I put it in terms maybe a little bit more common, if I said you have 9 inches, okay, and we've already established, or we already know, that 1 foot equals 12 inches, okay, which means that we would say 12 inches on the bottom, and we'd say 1 foot on top. And 9 divided by 12 is 3/4, 0.75 feet, okay? So you divide 483 by 1 times 10 to the 9th. So you plug that into your calculator, and you probably come out with something like 4.83 times 10 to the negative 7th meters, okay? So you have to make the conversions correctly, because wavelength won't always have the same units. It won't be in agreement with the speed of light. Nu, which is that V, the nu is equal to its units are in 1/seconds, which is the same thing as hertz. Hertz and 1/seconds are the same thing. So don't let that fake you out on the test, because it will say hertz for some of the questions instead of 1/seconds. Okay, give me one more second. Apparently, I need to send some direct invitations to people for this. And I think that if I invite them, let's see. I'll invite them to Pre-AP and they can get the link. My apologies for I think these are the last people. All right. Let's hope that works. Okay. So the next thing I'm sure would be great if I showed you guys an example. So let's go to the next page here. Open one up, and I think that we had. I'm just going to use something from our notes. Question is, what did I do with it? There we go. Okay. So we had a question where there was we had 101.1 megahertz, okay, and we want to calculate the wavelength. So this is new. What is the wavelength? So we have C is equal to wavelength times nu. And we have this, we don't have this. So if we isolate that, wavelength is equal to C divided by nu. So that's equal to 3.00 times 10 to the 8th meters per second divided by, and 101.1 megahertz. Now this is, since we want hertz, we want 1/seconds as the unit, because you see that's the unit here. It gives us that 1 megahertz is equal to 1 times 10 to the 6th hertz, okay? So we make our bridge, 101.1 megahertz. And we need to do the conversion here. And megahertz is here, so we have to use this on the bottom, these units on the bottom of the next step, so that they cancel out 1 megahertz and 1 times 10 to the 6th hertz. So when we multiply all that out, we end up with 1.011 times 10 to the 8th hertz. Okay, and then we can just put that on bottom here, 1.011 times 10 to the 8th, and might as well make it 1/seconds now, because they are the same thing, and this makes it a little bit easier to deal with. These 10 to the 8ths will end up canceling out, which is kind of nice. So you end up with a 3 divided by a 1.011, right? The 10 to the 8ths will cancel out, but if you put it in your calculator, you'll end up with a wavelength that is equal to 2.967 meters. And those are pretty long wavelengths. Radio wavelengths are very, very long, okay? So that's one example of how you would need to do that. Other things that could be happening in that essential skill number 1 is you should know that there's another equation. E is equal to H, which is Planck's constant, times oh wait, I'm not doing that right. Yeah, I'm sorry. E is equal to H times V, and for that one, E is we don't know that when we calculate that one, but H is our constant for this one, and that's 6.63 times 10 to the negative 34th joules times seconds. Okay, and what will most likely happen on more of the, maybe one of the more difficult questions in the test, will be asking you to, so much fun, a little substitution in regards to your two equations here. Okay, and we see that the V, is the same in both equations. So you just have to isolate the V. So then you get this V, the nu is equal to C over lambda. Okay, and then you're going to plug that into the V here, so that you get E is equal to H times C over lambda. Sometimes you'll see it written as E is equal to HC over lambda together. And so those are situations in which maybe frequency is not involved, but you're given wavelength, and you're going to have to solve for the amount of energy in that wavelength. Or maybe you're given the frequency and you end up having to find energy. So frequency, you solve for lambda, which is wavelength. Once you have the wavelength, you can plug that in. Because the really interesting thing here is that, of course, these two right here, H and C, are both constants, right? Here's one constant. There's the H, there's Planck's constant. And here's the C. This is the speed of light. This is the other constant. So with two constants in there, you can see a direct relationship between energy and wavelength. So kind of interesting. All right. So that's the first essential skill. So let's go ahead and move on to the second essential skill. I haven't seen any questions popping up over there, so I'll just keep going. All right, the second essential skill, let me go ahead and I'll pull back and share that. So the second essential skill is students should be able to write electron configuration and noble gas configurations for an element. This is actually fairly easy. I think that most of you are probably getting it, but I'm going to share it or going to go over it with you because I want to make sure that you get it. So let's just pick some random element that I like to talk about. Let's do phosphorus. So this is essential skill number 2. Electron configuration. We're going to do phosphorus, which has 15 protons, and we're just doing we're doing it in the table. 15 protons and 15 electrons, since it's a neutral. So that's how we're going to determine the electron configuration. And if you remember, there are 4 regions to the periodic table. There's S, which has just 2 electrons. There's P, which has 6 electrons. There is D, which has 10 electrons. And F, let's put it right down here, F, which has 14 electrons. Okay? Now that I'm thinking about it, I wonder if I could, maybe I could show you a periodic table that has that. I don't know why I didn't think of this sooner. Let's see if there's a, yeah, I think we have one here. Oh, it's not very big. Let me see if I can make it look bigger. And no, that's a terrible one. You guys aren't seeing what I'm looking at, which is just fine because it's not that exciting. There we go. Okay, I'm going to share this with you so we can see it, and then it'll be easier to talk about it. Okay, so I'm going to make it a little bit bigger. All right, so you can see that 1s1 and 1s2, the helium is still part of 1s because it's the second electron, so you move it over to, next to hydrogen. That's 1s2. Here's 2s, and there's 2 electrons there, and then you go over, it's like reading a book. You move to the left, and the 2p, 1 to 6. And then 3s, you start over on the left, and you work your way across, 3p to 6. And then 4s, and then when you get to the d's, of course, it is 1 shell below the shell that it's in. So it's in 4, but D is a lower energy level than S. So you need to drop down 1 when you're writing it, 1 to 10. Then there's the P's. And when you get down to 6, then you drop down 2 energy levels, because as the atom gets bigger, it has some space below it that it can backfill. And that's what's happening there. So it's dropping down a couple energy levels to backfill space, and then moving back out to fill up the rest of the atom. Now, the outermost electrons, or the valence electrons, are always the s and p orbitals. You'll notice that the transition metals are always below the outermost energy levels. So really, the number of valence electrons for all the transition metals would be 2. So even if we're not going to ask you this, but even if you're in the lanthanides and actinides and you're in 4F whatever, you still only have 2 valence electrons because that's within the 6th energy level, the 6th shell that's way out there. Okay, so you need to know, and we're not going to pick one within the lanthanides and actinides, but we could pick one in the 6p range, and you would need to write out the whole thing: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, on and on and on, and then be able to do that in the noble gas configuration. one of those mean things we do sometimes. So, but for right now, I want to do just the basics. So let's go back to our, we are going to go back to the Google, the bamboo pad, and we're going to do the one for phosphorus. Okay, so phosphorus has 15 electrons. So we start going, we have 1s2, 2s2, that gives us 4 electrons, 2p6, that gives us 10 electrons, 3s2, that gives us 12 electrons, 3p3, and that would give us our that would give us our 15 total electrons. If we were to go back to that picture for a second, you will be able to see that right here, 3p3, this is where phosphorus is. In the third energy level down, 3 elements in from the left. That's exactly where it is, and that is phosphorus. Makes it pretty easy. Okay. Now, if we're going to do the noble gas configuration, you have to do the noble gas from the row above to start off your noble gas configuration. You cannot pick one in the same row. You can, so if I'm asking you to do the noble gas configuration of a noble gas, you have to pick the noble gas from the row above to write it. So what is the noble gas that is in the row above? And I believe that is neon. So let's go back to our let's see. Oops. All right, so the noble gas configuration would be neon. So that's, and we put it in brackets, and everything up through here. And that's 3s2, 3p3. So when we put the noble gas in brackets, that's the entire noble gas configuration in brackets. And it comes to here. So pretty straightforward. Okay, before I move on to the next one, I just want to mention that you could be, if you click around a little bit, you can see that you can ask questions on, there's a Q&A app it's called, but I'm looking forward for you guys to ask questions about things, and no one's asked any questions yet. So I'm just keeping over this stuff. This might be basic for you, and it's not in-depth enough, which I can understand. So ask a question that's more in-depth. Otherwise, I'm just going to keep going. All right. So the third essential skill, I'll pick up the assignment sheet to look at that again. Students should be able to identify elements or ions based upon their orbital notation. So I did have some students ask, well, how are you going to know? Because they could have the same orbital notation. So I will have to tell you that. And so I'll give you an example of what that might look like. All right. So let's say that an orbital notation is, if you don't remember, that's the boxes. So this is 1s. This would be 2s. Here's 2p. Okay. So let's say I did this, and I might say, let's say I did this in a multiple choice, and let me change so you guys can see the arrows. So you have to fill, when you fill them up, the off-bow rule states that you have to start with the lowest energy first. Hund's rule states that you have to put 1 in each energy level first before, or I'm sorry, each orbital first before you can add a second electron. And then the Pauli exclusion principle states that you can't have them both going in the same direction. So they can't have the same, they can't be in the same location, basically. And you can see that these arrows are in opposite directions. If I put this arrow also going up, that's a violation of the Pauli exclusion principle. So I can't do that. So I'm going to take it off. Okay. So what I might do for a question is I might say, okay, which atom or ion is this? And I'll give some examples. So this is you can see right here that this could be a noble gas because it's got 8 in the right up here in the P, the S&P, it has 8 valence electrons. So it could be a noble gas. It also could be an ion. So it could be neon, it could be something like that. But let's say I gave you, is it helium? Is it chlorine 1 minus? Is it oxygen 2 minus? Or is it something even crazier like K plus? Okay, which one is this? And so you look at that, well, helium only has these two right here. Chlorine 1 minus it's up in the 3rd energy level, and K is actually in the 4th energy level. And there is no way it could be any of these 3. And it just so happens that the only ion it can be like is O2 minus. So that's if the multiple choice. We might ask you to write the orbital notation for one of these. We might ask you to, like if we said, what's the orbital notation for K plus? Or we might say, you know, give you some choices and say which one is a violation of the Aufbau rule, which one's a violation of Hund's rule. So you have to be able to identify, you know, if, let me give you an example for each one. So if I did this right here, and then I jumped up here, like that's a violation of the Aufbau rule. Okay. If let's say I did this, and then I did this right here, that's a violation of the Hund's rule because there has to be one in each orbital before you can stack up. This, as I mentioned before, is the violation of the Pauli exclusion principle, and they're both facing up like that. All right. So that's the 3rd one. Oh. Okay. When are we going to get to the part on POGL where we have to figure out when we are? Okay. So I'll take a break from the essential skills for a second. All right. So I select this, and Stephen wants to know when we're going to get to the part of the POGL where we have to figure out whether the stuff can break the carbon bonds. So Stephen, if you'd been paying attention, you would have noticed that I was going through essential skills, and that was not one of the essential skills. So we were going to get to it when somebody asked it. So now that you've asked it, we can get to it. So good of you to ask. Otherwise, we never would have gotten to it. All right. So let me pull up the. I'm going to screen share. Hold on a second. I'm going to screen share it. There we go. Okay, so I don't remember right offhand which picture it was. Let's see. I think it's I. It's this Roman numeral 2, problem 3I. Consider that the bond energy of a carbon-carbon single bond found in organic compounds is 347 kilojoules. Would X-rays and or radio waves be able to disrupt organic compounds by disrupting organic compounds by breaking carbon-carbon single bonds? Why or why not? Okay, so it wants to know if X-rays or radio waves would be able to do that. If in order to be able to do that, you have to know kind of what X-rays and radio waves, what their wavelengths are. And so you would need to look back at, let's see, here's the thing up here. So you could look, oops, sorry, radio waves, the wavelength are about 10 meters, or X-rays are down here at like 10 to the negative 9th meters. And so if we look back here, if they've given you the energy, you need to calculate the wavelength. And so earlier in the review, I gave you guys the formula for how to get the equation that relates energy to wavelength. And H and C are the constants. So you can isolate wavelength from this equation. So wavelength would be equal to HC over E, which I've done over here. Okay. So then you take your 347 kilojoules, and if you remember, Planck's constant is joules times seconds. So you're going to need to put them in consistent units. So you convert 347 kilojoules to joules, and I think I was kind of hoping you guys would have, I think it probably talks in there some way, but remember that 1 kilojoule equals 1,000 joules. Oh, there it is in the G of problem 3. 1 kilojoule equals 1,000 joules. So if that's your equality, and you're given 347 kilojoules, you know that kilojoules has to go on the bottom of the next step. Kilojoules will cancel out. You multiply them together, you get 3.47 times 10 to the 5th joules. So that's your E, that's your energy. That's going to go on the bottom of your problem. Your constants are on top, 6.63 times 10 to the negative 34th joules times seconds. Your speed of light, 3 times 10 to the 8th meters per second. And seconds cancels out and joules cancels out, leaving you with meters. And the wavelength is 5.43 times 10 to the negative 31st meters. So if you look up at your thing, 10 to the negative 31st meters, where does that fall in your spectrum? That is way, if you're looking at wavelength up here, it's way, way small. So it would take quite a bit more energy to break those carbon-carbon bonds. So the answer to I is no. And wavelengths the wavelengths are so much smaller, which would be very, very, very high energy. But hopefully that makes sense to you. Okay, the next question that we have up here, the answer key for the electron configuration practice worksheet says that the abbreviated electron I should just select it. All right. So the question from Holly, the answer key for the electron configuration practice worksheet says that the abbreviated electron configuration for silver is krypton 5s249, but the orbital notation simulation says that, oh, okay, so technically the 4d10 5s1 is the correct one. That is an exception to the rule because, let me share my Bamboo tablet again. Okay. It's really just for copper and chromium mostly. I'm not going to actually, I'm not going to have you guys, you don't have to do this on the test is what I should say. Let's say you're filling, I'm just going to use orbital notation as an example. Okay, so here's the S, and then here's the D. And D is a little bit lower energy, and then P, right, is up here. And D is down here. 2, 3, okay, 1, 2, 3, 4, 5. Good, all right. So once you filled in the S, and you start filling in the D's, once you get to here, okay, it has this lower energy level. We said before is D. This is P up here. This lower energy level will make the atom more stable if all of these are half filled, which means that in order to get half filled, sometimes it'll borrow one from the S when it's doing this. Okay, so that's when you move across. Let's say you're moving across and you get to chromium or molybdenum in your transition metals. And then when it starts filling up again, it's gonna start by adding electron back to the S, and it's gonna start adding them here. And once you get to copper or silver or even gold a little bit, instead of just leaving this here, it's gonna borrow from the S again and add it here to make it fully stable at the D level before it adds again to the S. So for really the only two exceptions that are going to be tested on, that potentially could be tested on, are copper or chromium. And I have to be honest with you, I'm looking at the test in front of me right now, I don't believe we're going to test you on that. So, so I don't want you to stress about it too much. If it were on the test, I would be fine with a 5s2 4d9. I'm okay with that. Technically, 5s. Oops, it's a horrible drawing. Technically, 5s1 4d10 would be the correct way to do it, but if you do this, you're going to get credit for it. Good question. Okay. The next question is, Kiki, can you define emission or bright line spectrum? Sure. So the emission or bright line spectrum means that a lot of times they burn the element. So you know how we did the flame test? Bright line spectrum. I should write this down, or emission spectrum. Okay, so when we burn those elements in the flame test, what ends up happening is that you could look through a grating. Let's pretend like this is a grating right here, and there will be lines, and it'll be the whole Roy G. Biv. In fact, I'm going to write it in black above so that you guys get it. Roy G. Biv. And it's specific to an element. So let's say there's a couple red lines here, and sometimes they're thicker lines. If I were to make this really thick, sometimes there would be like a thick line right there. And then oops. Then there is we go back and you know, maybe there's an orange one here, and maybe there's no yellow. Maybe there is we go straight to blue. And we'll make it a thick one here too. Maybe there's some thick ones there, and we work our way all the way over to, you know, violet is right there. And so that would be an emission spectrum right there for a specific element. Sometimes we have gas tubes. You can have gases, not only the noble gases, but maybe hydrogen, or they've made vapor mercury or vapor. I'm trying to think of some other ones that we might be able to show, hydrogen. And so they'll have this emission spectrum. And the emission spectrum, the bright line spectrum, is specific to an element. Sometimes they can look through these spectrum and they can identify several different elements by overlapping and seeing, okay, these lines we know belong to this. So like maybe identification of the elements in a compound. This is basically how they identified the existence of helium. They didn't even think about to look at our Earth because it doesn't combine with anything. We don't know where it is, and so we didn't ever burn it. But we saw that helium. We saw these lines coming from the sun, so we thought there was an element in the sun that was not on Earth, and so we called it helium for Helios for the sun. So and then we eventually ended up finding it here on Earth, but we had already named it helium. Kind of interesting, but that's what a bright line spectrum is. All right, Serene. Your question. What is the approximate difference in magnitude between a microwave and an X-ray? That's a good. So I'm going to share back the POGL, and we're going to look at the scale here, the electromagnetic radiation spectrum, and microwave and X-ray. So microwave is somewhere in the middle here of 10 to the negative 3, and X-ray would be somewhere in the 10 to the negative 9. So, I mean, this is kind of like a math at that point. Let me just do the bamboo paper then. So if we have 10 to the negative 3, 10 to the negative 9. Each time, or each 10, it's a magnitude of 10. So there is a 6-fold magnitude difference. You could do something along. If you're going to do this, you probably should divide one by the other. So if you did 10 to the negative 3 divided by 10 to the negative 9. And in math, you may or may not have learned about when multiplying or dividing exponents. When you divide them, it's the same thing as subtracting. So 10 to the negative third minus negative 9, which is really just adding a positive end. So it's negative 3 plus 9 gives you a 10 to the sixth difference. And so that's your magnitude difference between X-rays and microwaves. And these were the microwaves, and these were the X-rays. So I hope that answers your question there. I am super excited that you guys asked questions. That is very cool. Okay, so we only have a few more minutes left, and so I thought I would do the last essential. And the last essential skill, if we look back at our assignment sheet, has to do with percent abundance. Students should be able to calculate percent abundance and average atomic mass for elements. And I think this one kind of tripped people up a little bit. So I will share the Bamboo sheet again. And we'll go to the next page here. Okay, so there's a couple ways to do this. And you saw it on the worksheet. So we could ask you to find, like an easy way would be find the average atomic mass. So that's the first way. The second way is to find the percent abundance. And that's way number 2. And I'll probably end up testing both ways on the test. And really, it all comes down to this formula, right? So it's the mass number, or it's the average, it's the whatever the atomic mass. We'll say it's the atomic, what would you call it? Atomic mass, actually. So atomic mass times percent abundance plus atomic mass times percent abundance divided by 100 is equal to the average atomic, you know what? It'd be easier if I write, just so our abbreviations, average atomic mass. Okay? And so it all comes out of this. And percent abundance, whenever you have 2 elements, I just make it X and 100 minus X, because it's a percentage. So that's the easiest way to do it. If we did, I'm trying to think of one that's fairly easy and quick because I don't have a lot of time left for this. There was number 6 on, let's do that. Let me just show it to you. Okay, that's probably a little bit hard to see, so I'm going to make it bigger. 6. A certain metallic element has 2 stable isotopes, M45 and M48. Given that the atomic weights are 45.0010 and 48.0014 respectively, what is the percent abundance of the lighter isotope if the average atomic weight of M is 47.2002? So the way that you would set this up, now that we've seen that, is, let me share that. I'm not going to go through the whole solution, but I'll show you the setup. So number 6 would be 45.0010 times X, okay? And it wanted to know the lighter isotope, so that's easy. We'll just, X is the lighter isotope. plus 48.0014 x minus 100. So if I needed to eventually find out what the all divided by 100, and that's all, and I didn't give myself enough room. I have a hard time writing with this, I gotta be honest with you. It's equal to 47.2002. So you just solve this for x, right? That's all you're gonna do, solve for x. You're gonna, you multiply both sides by 100, and then I forget what words you guys use, but you multiply the 48.0014 times x and times 100, and then you're gonna add the subtract that 48 whatever 100 from both sides, or add it to both sides. I can't remember. And it's a negative, so you're gonna you add the negative to both sides, and then you just solve for x. I mean, it's algebra. I'm hoping that by now you guys are able to do the algebra. When I did it, my x came out being equal to 56.6%. For that was the percent abundance of the silver 107, which makes sense because with the not the silver, I'm sorry, the M45. Did I do that right? Oh, no. I'm sorry. I was looking at the next question, the silver question. Haha. No, that's not what I got. The X I got was 26.70%. Okay, I'm sorry. With the mass being 47, it's closer to 48 than it is to 45. So it makes sense that 45 would be a smaller percent abundance. Okay, so those are the essential skills. I'm hoping that that answers most of your questions, or it's a good review. The main thing is that you guys come in with questions. The essential skills should be easy. It's usually the other stuff that is hard and that students have questions on. And so I'll be happy to go over all your questions when you guys come in. So usually I would like to keep these, definitely less than an hour, 45 minutes to an hour at most. And my apologies, we started a little bit late. I have back-to-back reviews tonight, so I have to get going. Otherwise, I'd add a little bit more time here. The nice thing is your test isn't until Wednesday, so you can come in and ask me questions on anything that maybe you saw tonight or that you're working on that we didn't cover tonight. So thank you all for showing up tonight, and hopefully we'll work out the bugs. Spread the word that people have to be in Google+. They have to be in the community to get this link, because otherwise, if I share it outside of that, then I would get a lot of possibly random people joining, and we don't want that, or we prefer not to have that. All right, so thank you very much, guys, and I'll see you at school. Oh, bye.